The next project, I invite Aditya, who will tell us about their projects, how they use artificial intelligence in with operational challenges at ECMWF. So Aditya, the floor is yours. Thank you.
Hi all, I'm Aditya.
And this is Aditya.
Yeah, and we're CS undergrads from BITS Pilani. And for ESoC, we'll be building intelligent anomaly detection systems along with our wonderful mentors, Matthew and Peter. So coming onto the main motivation behind the project, why is this even important? So ECMWF's Mars servers handle millions of requests every day and serve several terabytes of data. And given the large scale and distributed nature of these requests, manually monitoring these systems for failure is difficult. And further considering the sheer stream of requests that come in, even a few minutes of downtime can be very expensive. So through this project, we aim to actually explore how we can use machine learning to actually predict and diagnose such events, such as downtimes, which might kind of delay our services. So it is also important to get an idea of the scale of events involved over here. So every day Mars serves at a million or so requests, and a downtime of even a few minutes might lead to thousands of requests going into a backlog, and that might delay downstream tasks for our clients. So we really try to optimize. So we're really trying to optimize on the kind of the bottom line over here. And of course, if successful, then we could apply similar methods to other operational services within ECMWF. So this was kind of a project with a very high impact and a very kind of a very central to the way ECMWF works. So yeah, so let's just move on to the data set and let's see what it looks like. So because this is a machine learning problem, we should actually just start with the data set. And right, so here we have a sample log file from Mars. And as you can see, we have, it contains several fields which are shown in bold and the corresponding values for these fields. So for example, this log belongs to 21st May and it corresponds to a retrieve request from the FTP5 prod database. So you can see we can use all of these fields to actually understand what's happening inside the log. But it is actually very difficult to do a direct analysis from these logs because one, we have a lot of these. So we have around 1.2 to 1.5 million logs like these every day, and each corresponds to one complete request. So like we have a lot of logs, and then we can't actually use these in any meaningful way. So what we did was we took all these logs and we filtered the interesting keywords from these logs and we aggregated them centrally so that we can use these to model time series of different variables, such as the number of requests sent in unit time, or the data retrieved, or the amount of data delivered. So we kind of aggregated all of these in a central database kind of, and then we can use these to actually make all the time series, and on those time series we can actually apply our the machine learning methods. So over here we have a sample time series, and what you can see is that after we have done the aggregation, we have a time series for a specific variable. So over here we have the time series for the retrieved volume versus the time, and right, and this is for the month of May. So right, and just for some information about this, so over here we had about 40 million logs to generate this whole time series, and its resolution is about 4 minutes. So each data point corresponds to logs that were taken across 4 minutes, and we have 11,000 unique data points. So 4 minutes for and about 31 days. So you may also notice that we have some red lines over here in the graph, and these corresponds to times that the Mars server was switched off. So maybe it was experiencing downtimes, it was having a maintenance period, it was having a planned shutdown. We don't actually know what it was, but it was something that had the server shut down. So we have these as labels. And now we can go forward and we can zoom into one specific section of the time series so that we can examine it in more detail. And so here we have zoomed in onto the 30th of April, which seems to have been kind of a rough day for our system because you can see we have a lot of issues over here. And in orange, we have those sets of windows that exhibit the anomalous behavior that we are actually trying to detect. So we have two such regions on this day. And the important thing to notice is that the orange regions, which were originally like labeled by us, match the actual downtimes of the Mars servers shown in red. So the story that you can kind of pick from here is that we suddenly see a decline in the volume of data being retrieved from the Mars servers, and this continues on for about an hour for the first case, and after which the systems are restarted. So we see the red line over there, which corresponds to a server shutdown. So that most likely means that the systems were restarted to correct the downtimes, and right, and then what we aim to do is we aim to perform near real-time checks for these types of issues to try to predict and detect these types of occurrences. So over here we took like kind of 1 hour to detect this. We try to we're trying to optimize this, so maybe 5 or 10 minutes. That would be the ideal case for us. And yeah, so moving on to the next slide, like one of the ways we go about detecting anomalies is by creating KPIs, which stand for key performance indicators. And here we have generated a sample KPI, which corresponds to an inversion of the original time series, which we saw earlier. So this is interesting, as we can see that the peaks in this time series, which correspond to declines in the number of bytes retrieved as we're doing an inversion, they align very well with the actual times when we had an anomalous behavior. So it's very easy from this for even a human to understand that, okay, these were the times when you actually had an anomaly. And great. So now I guess like Aditya can go over the various machine learning methods that you tried over the data set.
Yeah. So now just to start off, so the KPI was a basic example of how you can detect anomalies. So whenever the KPI scores were high, that indicated an anomaly, but that was a trivial one. So now moving on to the machine learning methods that we started. So once we generated the data, we had around 100 time series corresponding to various keywords and filters. So in this case, FDB5 prod was one database. Similarly, we had something for Mars OD and Mars ER and so on. So then we started applying the methods directly. In general, time series anomalies can have two kinds in a broad way: point anomalies and contextual anomalies. Point anomalies are sudden changes, like a sudden drop or rise that differs from the existing pattern, but it lasts for a very short amount of time. Contextual anomalies are shifts over longer time scale. Suppose you're having a possible server slowdown, or there's a resource starvation in any particular resource, then your server will slow down over time instead of one particular sample, but it is still an anomaly overall. Since both of these are very different, we need different algorithms to detect them, but we plan to integrate both of these into a final anomaly detection system. So how do the anomaly detection methods themselves work? So there are three general ideas, all based on the fact that an anomalous pattern will be really hard to predict ahead or reconstruct as such. So one way would be to just compare each time series window, every new time series window that comes up, with the windows seen previously. So anomalous windows generally have a very large distance or difference from previous time windows. So this works well, especially while detecting contextual anomalies. With a sufficient window size, you can easily see how a contextual anomaly is different from the previous time windows. The next thing we do is we build models that are trained to reconstruct a window based on a general pattern. So these models, so we use both autoencoders and GANs for people who have the knowledge. These models can easily reconstruct data that occurs in a regular pattern or is part of a normal distribution of data, but it cannot do the same for anomalies. The third thing we try is predicting the expected pattern based on previous window information. So in this case, we just forecast what's going to happen for the current duration. And if it does not correspond to what we forecasted, then we can have an idea of how anomalous it is. So for all of these, we both use statistical models and as well as standard machine learning and deep learning models. In deep learning, we stick to mostly LSTMs and combine them with the ideas of VAs and GANs. So why is this a difficult problem? Until now, it seems like looking at the KPI that we were able to detect all the anomalies without much trouble. So firstly, the anomaly distributions are very sparse in the existing server log data. For example, we had around 8 to 9 anomalies in the whole month of May, and considering each point that we sampled as anomalous point or not, we had only 1% of the total time series being an anomaly. So learning generalizable concepts, or just learning concepts that you can apply later from a small number of points, is if you have very little data, is a hard task in ML. Further, several of the points that we see that might seem to be anomalies, maybe a downtrend in the time series, might just have a benign cause, like something like a plant shutdown or a system update. So these things are stuff that we don't want to catch, because creating false alarms will just lead to people having to check again and again. And further, anomalies in the positive direction. So supposing you have the servers performing much better than expected, we don't want to catch those. So reconstruction based models sort of struggle with that a bit. Finally, the log files are generated only after the corresponding requests are completed. This creates a minor issue, because when there are ongoing requests, those have the most recent information. So we fail to get the most recent information about the time series. Say the last 5 minutes, we don't have an accurate picture of what's going on. So this makes the real-time setting slightly trickier. So as of now, we've applied several machine learning models and deep learning models, but I won't be able to go into the details due to a lack of time. But here are a few results we have. So this, just going through the methods and the results so far. So this is BANPI. BANPI is a simple algorithm. It's used for change point detection. So it detects whenever a time series deviates from an existing global pattern. As such, it is more useful for detecting longer anomalies of the contextual kind. So in this graph, you can see out of the points that we have labeled, the red lines and the blue lines correspond to the anomalies that we were provided, as well as anomalies we have labeled ourselves. BANPI seems to detect the larger anomalies, say the ones around 21st and 27th and so on, fairly well. You can see a spike in the anomaly scores. But for the smaller anomalies, it has a slightly harder task. So for that, we have one more method known as Luminol. So Luminol is a sliding window similarity based anomaly detection algorithm. So it falls in the paradigm where we take a window and compare it to the previous windows. And it is more suited for detecting short-term anomalies. So here we seem to be catching more of the anomalies between 3rd and 7th. Since time series generally come with inherent noise themselves, none of these methods are a crystal clear predictor, but the idea is through combining these models through an ensemble, or through gathering the predictions in sort of a combined way with, say, if conditions or thresholds, we will be able to reduce the false positive rate significantly. Then moving on to Telemanon. Telemanon is a deep learning method that uses time series forecasting. So in this case, it forecasts the window that's going to be the most recent one, and then takes a comparison with what actually happened. And then based on the ratio of what happened, we sort of get an anomaly score. This is more useful in a real-time setting. So when we combine the techniques together, some methods will be more relevant in a real-time setting, but others will also add confidence to our model that this is an anomaly. Finally, moving on to Donut. Donut is based on a LSTM VAE based architecture. So we try to build a reconstruction of every time window, and supposing we're unable to reconstruct a time window well, that indicates that it's been out of distribution and is likely to be an anomaly. So having a look at this in the training set, the validation test set is a more clear picture. We don't have too many labeled anomaly points, so verification is a bit of a hard task. But, so here you can see the anomaly score, the lower the score, the higher the anomaly likelihood. So this is one method that we have. So this is the current progress we have right now. So for further work, we plan to implement and train more machine learning methods, especially on more data. This will help us refine whatever we have and reduce the false positive rate. Even if we're able to say catch half or 2/3 of the anomalies that occur, it will lead to a significant improvement in the system. We aim to adjust the algorithms to focus on negative anomalies, possibly to tuning a loss function and changing thresholds, and to ignore the peaks. So if you were to look at Telemanon seems to have picked up a few peaks as part of its anomaly. Then we plan to combine these into an integrated alarm system. And finally, we plan to package everything into a directly deployable and easy to run format for future use and extensions. So I'd like to say a big thank you to our mentors, Peter and Matthew, as well as Victoria's Manuel and all the people, wonderful people at ECMWF have provided data, continuous guidance, and kept us going. Thank you. So any questions? I guess depending on the time situation, we can take them up later.
Thank you, Aditya, and thank you, Aditya. Yes, I would say we take up the questions later, but also just knowing the volume of the Mars log files, it's tremendous and amazing what you already did in the project. So quite impressive.